Look at a jagged rock pulled from the earth. Then look at a gleaming mechanical gear. The gap between them seems almost impossible to cross. It's easy to look at a factory floor and see industrial manufacturing as a chaotic collection of heavy machinery violently hitting metal until it takes shape. But producing an engineered component actually requires a rigorous, deductive set of decisions. Every step to physically manipulate that matter is calculated. To navigate this, we use what you can think of as a taxonomic tree of manufacturing. Looking at this diagram, the very first split defines our entire approach. The left branch is primary shaping, and the right is secondary processing. Primary processes dictate the gross overall structure of the object. Secondary processes define strict dimensional tolerances and prepare it for final assembly. By navigating these branches, engineers use strict physical laws to systematically design the entire life cycle of any object. This framework organizes hundreds of specialized machines into a single logical sequence of material transformation. Let's start on the left side of our tree, primary shaping processes. The first way we establish physical shape is through a phase change, specifically casting. Casting utilizes extreme thermodynamics to bypass solid resistance. By raising the temperature until iron hits a fluid state, we pour it into a negative space to cool and solidify into our target shape. But if we want to avoid turning the metal into a liquid, we move to the alternate branch, solid-state deformation. This brings us to forging. Here, we heat the solid iron just enough to make it malleable, then apply localized kinetic force, usually an immense industrial hammer, to literally crush and compress the metal into a new size and shape. When we need bulk materials scaled up rapidly, we rely on continuous deformation processes. Rolling is one method. We continuously pull glowing hot metal through dual compressive cylinders, steadily reducing its thickness into standardized sheets or pipes. Then there's extrusion. This involves forcing the material under immense pressure through a specific die, like a star-shaped hole, yielding a long, continuous part with that exact cross-section. These primary processes excel at defining the rough outline of the component, but they lack the finesse to hit exact engineering tolerances. Primary shaping is a blunt force negotiation with physics. We use immense heat and massive pressure to set the macro geometry, laying the physical groundwork for precise refinement. Now we cross to the right side of our tree, secondary processes, starting with the machining subbranch. Machining is subtractive. We apply localized shear forces to carve away bulk material, peeling off exactly what we don't need to reach absolute dimensional accuracy. A foundational subtractive method is turning. We mount the workpiece on a lathe, rotating the spinning cylindrical metal against a stationary cutting tool to shave off the outer diameter. When it comes to making internal holes, there is a strict functional difference between creating the initial void and refining it. This diagram outlines drilling, plunging a bit down into metal to create a hole, leaving a rough inner wall. We correct that through boring. A single point tool travels down that drilled hole, shaving a microscopic layer to achieve a perfectly precise diameter. The same subtractive logic also produces specialized surface texturing for functional grip. In a process called knurling, we press a heavily patterned tool into the rotating rod, physically deforming the outer surface into a rough, diamond-shaped texture. Subtractive machining successfully bridges the gap between raw shape and precise functional dimension, but the cutting action leaves a mechanically sheared surface that requires one final level of treatment. We move one level down the tree to the surface finishing branch. Finishing processes target microscopic surface roughness. The goal is to either maximize aesthetic shine or create a perfectly frictionless face for mechanical operation. We achieve mechanical planarization through lapping. By introducing a fluid slurry of tiny abrasives and applying rotational friction, we grind microscopic metallic peaks perfectly flat. We scale that abrasive action up with polishing and buffing. This is how we achieve the high reflectivity, mirror-like finishes required for consumer assemblies like motorcycle parts. But finishing also holds a major procedural shift, moving away from mechanical friction and turning to electrochemistry. This is electroplating. By running electrical current through chemical vats, we force suspended metallic ions, like cadmium or gold, to bond superficially to the base workpiece. This chemical addition alters the exact surface properties of the component. It adds strict corrosion resistance or premium aesthetics without disrupting the underlying machine geometry. Surface finishing represents the absolute limit of dimensional control. Once complete, the individual workpiece has finished its physical transformation. The final sub-branch in our taxonomy is joining and assembly. Engineered products are rarely monolithic. They almost always require the permanent synthesis of discrete, independently machined parts. For high-strength joints, we use welding. We apply extreme, localized heat to actually liquefy the base metals, fusing thick industrial structures directly to one another. But welding requires massive heat input, which will destroy highly delicate components. That's where soldering comes in. We use low heat, melting only a separate filler alloy. The delicate electronic base materials remain completely solid. Intermediate processes like brazing exist along this same spectrum, allowing engineers to balance the structural strength of the joint with the amount of heat the materials can tolerate. These joining processes scale our thermodynamic principles up or down, unifying separated geometries into a single cohesive machine. Looking at this complete diagram, we can finally see the entire manufacturing taxonomy mapped out. To see how this framework functions in the real world, we can trace the exact life cycle of a specific high-precision part. Based on the material's necessary phase, we make our initial node selection, taking a raw billet and running it down through the forging branch. The path crosses into secondary machining. The piece moves precisely through the turned node, then drilled, and finally bored to clear tight tolerances. Finally, it drops down into finishing, running through the lapped and electroplated nodes before resting at the bottom as a polished, completed mechanical gear assembly. The route is never arbitrary. Node selection is a rigid deduction dictated entirely by physics, phase changes, and shear forces. By mastering this classification system, engineers gain the exact blueprint to take raw earth and systematically manifest any design into a finished, functioning component.